All right, the first derivative test. What does it mean? Why do we use it? Where does it come from? Now, this is a topic that comes up in Calculus 1, but we see it again in Calculus 3, and maybe in some other math courses. So, to understand this first, we have to get what the derivative really tells us. And you have to remember the derivative tells us how fast something is changing, or its rate of change. Essentially, it's the slope for a function. But a slope is usually a value, 3, 7, -4, or 1/2. The derivative is usually a function. Now, it doesn't always have to be a function, but it can be, which means that we can put different numbers in to get different values out. And the reason this is useful is because functions change, right? As we see on this visual example on the right, the derivative here at x equals 2 is 0.5, but at x equals 4, it's 1. Basically, the derivative is changing. So if something's increasing or decreasing rapidly, the derivative will be a large number, right? We see that as this function grows steeper and steeper, the derivative starts to increase. And same if it's increasing or decreasing slowly, such as over here, we'll see that the slope or the derivative at that point is quite small. Finally, if something is not increasing or decreasing, the derivative is 0. What's the rate of change of something that isn't growing? 0. If a population starts at 400 people and ends at 400 people, and the entire time it remained at 400 people, what's the derivative? What's the rate of change? 0. It's not changing. Same for speed. If you're going on cruise control, if you're going 60 miles per hour at 1 second and then 60 miles per hour at the next, how fast are you changing? Nothing, you're not. You're just going at a consistent 60. So let's apply that example here. What is the derivative from x equals 2 to x equals 4? So from here to here, what's the rate of change? 0, right? It's not changing. But let's apply this to this quadratic or this polynomial function, right? Where's the derivative equal to 0? Now, it may be tricky to spot, but if you guessed here at -1 and here at 0, you'd be right. Because we also have to remember that the derivative is a tangent line, right? And what's the slope of this line? 0, right? If you have a slope of 0, or it'll be flat and straight like this. So the key takeaway here is not so much this one, but here I want you to understand that the derivative is 0 at these peaks and these lows. Continuing, these points, we call them local extrema. Local because, or rather extrema because they're extreme, they're the highest or the lowest, and local because it's in the surrounding area, right? This is the local highest, but we can see all the way over here that something actually goes higher. So, but in the area, it's higher than all these points. It's the king of the hill. And same for this one. It's the lowest in the area, but we still see that there's some things that go even lower. So we call these a local extrema. And at these points, the derivative is 0. Now, a slight little side point. Well, it's actually kind of important. While the derivative is 0 at the extrema, just because the derivative is 0 at any point does not mean it's an extrema, right? So derivative being 0 does not mean that it's an extrema. But if it's an extrema, the derivative will equal 0. Got it? And this is why we have to test it, right? We can't just solve for 0 and be done with our day. And here's an exception of that. Right here, whoop, we see that the tangent line is 0. The derivative is 0 at this point. And let's check it, right? This is the function x cubed. We take the derivative. We get 3x squared. Set it equal to 0. At x equals 0, we know that the derivative is 0, right? Boom. Is there an inflection point there? Or sorry, a local extrema there? No, that's what we have to check. We have to check with the surrounding points. So we draw a number line. And what we call these points where the derivative is 0 and there may be an extrema, key point or key emphasis on maybe, we call those critical points. This is a term you have to get used to. So remember, critical points like that, okay, this is maybe an extrema, and then the extrema is, okay, we confirmed that it's the local highest or lowest. How do we do that though? Well, first we get this. We still do our first derivative and then solve it for 0. And we happen to get x equals 0 here. Now we have to check on the left and the right of this. We check for f prime of x, or the derivative. So let's choose a number to the left. Negative 2 is a nice and easy number. It can be any number. It can be negative 0.001. It could be negative a million. But let's do something easy. So 3 times negative 2 squared. It's going to give us 3 times 4, 12. It does not matter what this number is, all right? But it does matter if it's positive or negative. It happens to be positive here. And let's try that for a number to the right. Positive 2. So we get 3 times 2 squared. 3 times 4. Once more, we get 12. And importantly, it's positive. And the reason that matters is because think of it like drawing a mountain. If you want to draw a mountain peak, you have to draw up and then down. Or if you want to draw the bottom of a trench, you have to do down, then up. In math terms, the derivative is positive, then negative, or negative and positive. But if I draw positive and positive, that's not the top of a mountain, is it? Same way, if I draw negative and negative, that again isn't the bottom of a trench, is it? So we need it to be opposites. It has to be positive, then negative, or negative, then positive. Here, what do we see? Positive, then positive. So is that a maximum? No. And we see it here visually. It's not. It doesn't have a little hill behavior. The takeaways. Number 1, the derivative tells us how fast the function is changing. If it's changing fast, the derivative will be large. If it's decreasing, it'll be negative. If it's not changing at all, it'll be 0. Second, the points of relative highs and lows are called local extrema. This is called the maximum because it's the highest, and this is called the minimum because it's the lowest. Third point, and this is the really important one. The critical points are where the derivative is equal to 0. So, see if I can get this right. For example, the derivative is 0 here, the derivative is 0 here, and the derivative is 0 here. So we would call these the critical points. But are critical points necessarily extrema? No. Here we see that it's an extrema, it's a high, or maximum. Here we see it's an extrema, it's a low, or a minimum. But here, the derivative is 0, so it's a critical point. But is it a maximum or minimum? Is it a local extrema? No, it's not the highest or lowest point in the surrounding area. It's just flat. And lastly, this ties into the fourth takeaway. You have to check the points to the left and the right of these critical points to verify if it's an extrema, right? Or else it might just be a case like this, or like the case I showed you here, where it's not an extrema, but it is a critical point. Let's do some practice. So this is the graph of the function f of x. Graphically, you just tell me with your pencil, where are the extrema? So we see one here around negative 0.8, I'm not sure. We see another one here around negative 0.5. We see one here around 0. So those are the extrema. And those extrema will also be critical points. But a critical point will not be an extrema. I really want you to understand that. I'll write it down here. So an extrema, there will be a critical point. But if you have a critical point, you don't know if there's an extrema, right? I'm not going to say it can't be because it may be, but you don't know if there's an extrema. And on the right here, I have something a bit different. You see these a lot in AP tests and your class tests and homework. So let's go over it together. I've given you not the function of a graph, g of x, but it's the graph of its derivative, g prime of x. Knowing this, where do you think there may be local extrema? So let's think. We know local extrema come from critical points, and we know critical points are where the derivative is 0. Now, so we know that's, remember that. Or critical or 0 or undefined, right? But for this one, let's just do 0, right? Critical points are where f prime of x is 0 or undefined. So where do we see in this graph of f of x or f prime of x that the derivative is 0? Well, we see it here, where it crosses the x-axis. So you're going to want to get used to that. You're going to see a lot of things, they'll give you a nice little graph, it'll look something like this. And I'll say this is the graph of f prime of x. Where are the extrema? Or where are the critical points? Here, here, and here, if it's f prime of x. Now, if it's f of x, the base function, where are the extrema? Here and here. I really want you to understand that if you're given the graph of the derivative and they want you to find the behavior of the original function, you have to look where the points cross 0. And this really ties into knowing what the derivative means. You have to know that derivative is rate of change. Remember that derivative is rate of change. So if the rate of change is 0, what does that mean? We have a critical point. And that's why we look at the x-axis. All right, oops. Here's a function. Now we can see graphically, this is f of x, that the derivative or the extrema are here and here. But we can tell it's not really easy to see what this is. So we're going to have to do it numerically, or with calculus. So first we have our function x cubed plus 2x squared. Let's take the derivative of that. The power rule, we bring the exponent down and reduce it by 1. 3x squared, same here. 4x. There's an invisible 1 here, but I will. Remember that, it's implied to be there if you don't see it. So we set this equal to 0. And now what? We use a quadratic formula, but that's a bit overkill. Why don't we try factoring? We see that both of these have an x. So we do x, and then on the inside, we're left with 3x, right? Because 3x times x is 3x squared, so it's equivalent. And then 4. And now we're going to use some of our algebra, right? If we have two things being multiplied by each other and they equal 0, you can set them equal to 0 individually. X equals 0. That's one critical point. Remember, we don't know. And then here's another one. 3x plus 4 equals 0. These are critical points because we don't know. These are just simply where the derivative is 0. This stays the same. This we have to move the 4 to the other side and then divide by 3. And these are critical points. Now, if we look at our graph, we know that these are extrema. So you can get away with not doing the whole line test. But what about this one? We don't see any graph. What do we do now? So we have x to the 5th minus 3x cubed. We could graph it, but that might take some time. And why is there a need if we can do it with other ways of math? Let's take the derivative. Using our power rule, bring the exponent down, and then reduce it by 1. Same here. Sorry, that would be a 9. This would be an x squared. We set it equal to 0. All right, what do both of these have in common? I don't see any numbers, but I do see that the x squared is there. So we do x squared, and then we do, what's left on the inside? X squared, right? What's left on here? Well, we took out the x squared, so all that's left is 9. Set it equal to 0. Same thing as before. X squared equals 0. That's pretty simple. X equals 0. So it's our critical point. Remember, we don't know if it's an extrema, right? We just know the derivative is 0 there. That's all we know. And then we have 5x squared minus 9 equals 0. We turn this into 5x squared equals 9 by adding 9 to both sides. We divide both sides by 5. It's going to give us x squared equals 9/5. What do we do now? Oh, square root both sides. X is equal to, it's the important part, plus or minus, what's the square root of 9? What's the square root of 5? Okay, so you could simplify this, but I'm just going to turn this into a 3 and leave the square root in the denominator. You're not supposed to do that, but it's fine for the sake of testing. All right, so we have our critical points, and we don't have a graph, so we don't know if they're extrema. So we have 0, then we have 3, radical 5. All right, this one's going to take a while, and you'll see why. And then we have negative 3, radical 5. So remember, we have to check in between. We have to see if it's going up, down, what's going on. So let's choose a number between these. I would recommend using your calculator for this so you can see, all right, what on earth is this equal to? So we have 3 divided by radical 5. That's roughly equal to 1.34. And this is just going to be the negative version. All right, cool. So let's find some in-between values. Well, a nice and easy one is 1. This is negative 1. And not only that, so I'll put these in boxes to make it easy to tell because I can't change the color right now. I actually can't. And then what's something to the right? Well, this is going to be 2, and this is going to be -2. And now, unfortunately, we have to test all 4 of these values and see if it's positive or negative, positive or negative. Now, quiz, pop quiz. Do we test it in the original function, f of x, or do we test it in the derivative of the function? Think. We're trying to see if the rate of change is that whole mountain situation. Is the rate of change positive than negative, negative than positive, or some positive, positive, negative, negative that, isn't an extrema? Remember, trying to see if the rate of change flips from positive to negative. So, since we're trying to see if the rate of change is the one that's varying, we check the derivative. Now, I might run out of space here, but I'll try to keep it small. So, first one is -2. Let's get the hard one out of the way. So you can plug it either into the factored expression or this one. I think I'll do it into the base one. So 5 times -2 to the 4th minus, 9, -2 to the 2nd. All right, this is going to be 5 times 16. This is going to be minus, this is 4 minus 36. All right, 5 times 16. 80 minus 36, that is going to give us a positive number. So we know here it'll be positive. Now, interestingly enough, I could do it for 2. I can do it all over again. But what do I notice? This is an even exponent. This is an even exponent, meaning all negatives will be turned positive and all positives will stay positive. So if I put in 2 instead of -2 here, I'm going to get the same answer. So boom, we know this is going to be positive. And luckily, the same trick will apply for -1. So 5 times -1 to the 4th minus 9 times -1 squared. This will be 5 minus 9. That's much easier to work with. This will be a negative. And with that same trick, even exponents means positive stays positive, and the negative will turn positive. So we know this is negative and this is negative. All right, let's do a little mountain diagrams. Positive looks like an up. Negative looks like a down. What do we see here? Oh my gosh, look, an extrema. So we know that at this value here, there will be an extrema at -3 radical 5. Right? We see a little mountain. It goes up, then down. What about here? It goes down, then down again. What's up with that? Is there going to be extrema here at 0? No, there's no little mountain peak. And then we try the same trick here. Negative, then positive. Oh my gosh, there's going to be extrema. Is it a maximum or a minimum? It's a minimum, right? It's the lowest. Down, then up. It's low. So we know there's going to be one at +3 radical 5. So it was necessary to do this test, right? Because had we just, chosen all the critical points 0 and then the radical ones, we would have included 0. And is 0 an extrema? No, but it's a critical point. Let's prove this visually. Oops. Oh. As we can see, we see on the, -1.3, whatever it was, we see an extrema, a maximum, right? And then over here, we see a minimum. And what do we see at 0? Oh my gosh, one of those cases where it's a critical point, but it's not actually an extrema. All right, so I hope this helped, and thank you for watching.